Alright, so now that we have those three-dimensionless groups, we want to be able to create 100 points of experimental data that's normally distributed, and we want it to have a 10% error for the experimental, as an experimental error. And then we want to use linear regression and those dimensionless groups to be able to fit the relationship of the experimental data that we're going to create. So let's start with the things we're going to need to use throughout this this code. So first we're going to be doing numerical calculations, so we want to import numpy. And I'm just abbreviating it as NP. So then we also want to be able to make side-by-side subplots. So I'm going to use something called Plotly. And we're going to make those subplots. And we're going to import something on my screen. Okay. And then we want to be able to import those subplots, so we're going to make them subplots. And then we want to make graph objects, which are just in this case we want to make a scatter plot, and that's just a graph object. So objects, and I'm just going to abbreviate that as go. Okay, and then we want to use something called SciPy and use the package called optimize to be able to then import something called minimize, which I will get into later in this code. And that should be it for that. So now what we want to do is we want to create those 100 points for the plot. So let's start off with the Reynolds number. I'm just gonna create a variable called Reynolds, and then we're just gonna use numpy. And then we want to create those randomized experimental points. So that's this is what's going to mimic that. And we want it to be uniformly distributed. And then it's the range of the Reynolds number, which is given in the problem statement, is going to be from 2,000 to 35,000. So 2,000. And then we want there to be 100 points. Good. And now something similar for the Schmidt number. Still want those randomized points. But in this case, it's going to be from 0.6 to 2.5, and then we still want 100 points. So now we want to put in the Gilliland-Sherwood correlation, which is given in the problem statement as (0.023) times the Reynolds number to the exponent of 0.83 multiplied by the Schmidt number to the exponent of 0.44. And then we want to create 100 randomized points for that as well, except in this case, here, let's put this in first. we're going to put the local, which is just the average, to be around, centered at the Sherwood number. And then we're going to scale, and then from that average being surrounded around the Sherwood number, the Reynolds number and the Schmidt number will correlate with that because of that relationship that we just typed up here. And then we want to scale it, which just means that this will take into account that experimental error, which we want to have. Otherwise, we aren't really creating that variation that you normally would have with experimental data. So we want to have an experimental error of 10%, so that's just 0.1, and then multiply by the Sherwood number, because that's what we want to vary, and the rest, like I said, will follow. So now looking at this relationship and this that expression, we want to see that we can see that those coefficients or those exponents, they have values, and those values were found by Gilliland and Sherwood when they performed experiments with 9 different fluids. So now what we want to do is we want to put that equation into a linear form so that we can perform a linear regression. And then we want to replace those coefficients and exponents with variables so that we can find variables or coefficients and exponents that will fit our experimental data. So let's just put it in now to show that new equation. I'm adding this comment, and we're just taking the natural log of everything. Okay, so now we want to do something where I use numpy, ones like, and then we're going to do it of the Sherwood number. So now what this is going to do is going to create a shape like the Sherwood number, and so we're going to have 100 of that. Okay, so there we go. And now we want to put in the Reynolds number and the Schmidt number. So let's do that. This just takes the natural log. And now what we want to do is we want to do a column stack. So it's going to turn these one-dimensional arrays and stack them, so that it'll turn them into three-dimensional arrays as columns. So now this will become our design matrix. So let's add it in. So we want this. Should run that first. NP. Here, another parenthesis, and so we're going to add that column stack in now. And we're just going to set it to a variable of x, and that's just going to be our design matrix. All right, so now what we're going to do is we're going to show you what this looks like. Oh, that's an MP, not RE. So now if I want to show you the shape of this design matrix, I can just do this. And now we want to look at, we're going to add a transpose into this equation. So let's just see what transpose looks like. So we just do x.t, and that'll show the transpose. And so what you can see is that, maybe I should put the shape in. so that we can just compare the shapes. See, what it does is it just swaps the columns and rows. So you can see it's that 100 and then 3 and then 3 to and then 3 and 100. So let's delete these. So now what we want to do is we want to be able to find those coefficients for the expression. So the A, B, and C. So what we're going to do is we are going to set a variable of b, a lowercase b, to the matrix of those parameters. So what we're going to do is use numpy, and linear algebra is just that linear algebra that we're going to utilize. And then we're going to take the inverse of this transpose multiplied by the matrix. And by doing this on both sides, we're able to obtain the vector of the parameters that we want to find. And so by doing this, it's called the Moore-Penrose inverse. And so let's just show B. Okay, so this array. So let's look. So comparing these values, so we get the 8.3 for that Reynolds number, and then 0.46, which is pretty close to that Schmidt number. Then we have a negative 3.77. That kind of correlates to that coefficient over here, but we have to remember that if we we took the natural log of that first value, so we'll need to take the exponential of that first value in the array to get something that kind of looks like that 0.23. So it's similar to those initial values that we would expect. And that's good. Oh, thank you, Lacey. Perfect.